Welcome to the first lecture of stability of structure. So, first I will start with the little PowerPoint presentation, where I am going to tell you the history of structural stability, why structural stability is important and how the theory has developed, and at the end I will refer to you the refer some book to you which will be useful. And then of course, I will start with with the deriving equations and the theory, but before that I am going to use the PowerPoint actually. So, I am going to review stability of structure, its past, present and the theory, the chronology of development and then the retrospection, how the theory, how the subject developed, and who are the people who scientists who contributed, in the development. Okay. So, the chronology you are going to refer. So, this is based on a review by Bhajan, Professor Bhajan, who is one of the authority in this theory of stability, structural stability, and he has a book which is can be treated as Bible. Okay. So, he published a paper in International Journal of Solids and Structure on structural stability. Okay. He is from Northwestern University Civil Engineering Department. So, what overview of structural stability we are going to present here would include inelastic stability and elastic stability first, and then inelastic stability as well. Although in the course, we are going to restrict our discussion to elastic stability only, and that itself is the first subject. Then static and dynamic instability, the importance of nonlinear behavior. Initially it is linear, right? And formulation of stability using thermodynamics. Why the use of thermodynamics may be useful or appropriate for formulating stability problem, and then stability behavior of time dependent system like viscoelastic system and viscoplastic or rate dependent plasticity problem, and stability under fatigue and under fracture and damage, which is a combination of the geometric instability and then the material instability. Okay. So, you see there have been several failure that has triggered the quest in structural stability. Okay. Of course, 1940 is the Tacoma Bridge collapse was the very famous or notorious, whatever, that basically that happened on Tacoma narrow bridges in Washington, US, and it collapsed by aerodynamic instability. But even before that, that is most famous example, and then all of we are aware about that, and then when we studied in our school level, we have seen the the picture, and then videos are available everywhere to see how the collapse is happening. So, this is one of the little more complicated which we will cover at the end of our course, but that is definitely a very compelling example of studying why to study stability. Before that 1907, there was a collapse of Quebec Bridge in Canada over St. Lawrence River. Then 1978, collapse of a space dome in Hartford Civic Center in Connecticut, US, and then collapse of 1978 reticulated dome in College Theatre, Brookville, New York. There have been a collapse in Melbourne, Australia, which is one of the greatest industrial disaster. The collapse of a steel box garden 1970s, all of them involved, of course not the Tacoma Bridge collapse, but other involved lots of casualties and then death, right? And 1965 collapse of Ferry Bridge cooling tower. So, these are just few examples. There are numerous other examples. So, all this failure actually, so we have some learning from failure, right? That basically was the reason why I think this underscores the need for studying stability. Okay, why we need to have a very sound knowledge of structural stability. Okay, because we want to prevent this failure and we want to design our structure to be safe. Okay, so if you go the development of the as far as the development of the theory is concerned, you see it is very brittle, old. It is 1744 where Euler basically provided his very famous solution of buckling of an elastic column. All of us we have studied this buckling of column in our undergraduate course, right. That was way back 1744, okay, long almost like more than 200 years or more than even more. By the end of 19th century, along with other development, we have pretty much good, a reasonable understanding on linear elastic stability. That was all this problem was solved. Of course, nevertheless, because there are introduction of new type of structure or development of new materials, so we need to have, of course, the same solution, elastic stability solution for this applicable to these specifically these structures, right. By 20th century, extended the stability theory for nonlinear stability theory. So, our linearized stability theory has been extended to nonlinear stability theory, but let me tell you that today also it is mostly even all research we make use of the linearized stability theory. Nonlinear stability theory is not very simple and not very easy to do, and it has been shown that we can capture very useful information even with linearized stability theory. Okay. And they include large deformation and nonlinear constitutive behavior. So, it is basically geometric instability which is responsible, and we make use of the geometric nonlinearity to develop stability theory, but along with that there can be interaction with nonlinear constitutive behavior. That means nonlinear stress strain relationship of material is also important. So, that basically get along the geometric instability. Okay. Now, then by the second half of 20th century, you have a pretty good understanding of dynamic stability, non-conservative system, and then there are several intricate aspects what people started studying, post-critical instability, chaos, and then today the larger emphasis or even the research is concentrating on instability bifurcation under material instability, that means in the form of propagating crack front or the damage material which is damage plasticity, for example, concrete, some composites and others. Okay. So, the stability of column, frames and arches, you see these are the chronology of development. Euler's critical load was given 17th century, and then once this theory was given, there has been lots of doubt among the mind of people that they didn't they didn't believe that this whatever he has proposed is good. So, because there was lots of huge disparity between the experimentally observed critical load and whatever was given by Euler's critical load. Okay. So, that disparity was explained by Young in 1807 by using imperfection, the concept of imperfection, that means the initial curvature, okay, of the column was responsible for this. So, that today also it is acknowledged that imperfections plays a very important role in stability. Okay. We are going to study all these things. Okay. Then of course, later elastica was introduced, where large deformation of column has been taken care by Kirchhoff in 1859, you see, and then subsequently there are other important effects like shear deformation, effect of shear on buckling by 1889 by Engizar. And unfortunately, this was one of the reason, okay, lack of understanding of effect of shear on critical load was one of the reason for the failure of 1907 collapse of cubic bridge. Okay. Had we know these things, the effect of shear deformation would have prevented such collapse. Okay. Then for the frame, we have flexibility matrix method and then stiffness matrix method that were formulated. The problem with the flexibility matrix is that it gives inconsistent result, and sometimes it is they suffers from numerical instability. Okay. So, but then both of them were replaced by the modern finite element technique, which was developed around 1950s. Just see this approach, flexibility matrix approach 1926, and then the stiffness matrix by James, Leibsley and the Chandler 1935. Shortly after that, around 1950s or so, finite element was gaining prominence. Okay. And then they will replace these approaches. Okay. And then of course, those theory has been extended by other one dimensional structures like buckling of cylinder, high arches, rings. Okay. That was considerably more difficult, because you will see arches and others, they will have pre-buckling nonlinearity, and then it has been seen that many people who try to formulate it using linearized theory, they end up getting wrong result and inconsistent result. That is because all these things significantly affected by pre-buckling nonlinearity. But the first solution that has been proposed by Bushnich for 2-inch arch and then later it was corrected by Herbrink. Okay. And by 1917 70s, that for arbitrary statically indeterminate arches were understood. Okay. Then for the dynamic instability, for all the static instability, the notion of dynamic instability was given by 1893 by Lyapunov, Russian scientist. He generalized the definition of stability for dynamic systems. So, we will see that. And then there have been other systems like parametrically resonating column. A column, when it buckles, when it is axially compressed, subjected to axially compressed load, and then it beyond a critical value of that load, it will buckle. But you will see if the axial load is changing over time, that means it is a fluctuating, it is oscillating, okay, with some frequency. Then there is something called parametric resonance things, okay, happens where the lateral vibration have a double frequency than that of axial frequency of the column, right. So load should for the resonance to occur, that should be 2 times of that frequency. So that is solved by using Matthew differential equation by Rayleigh in 1894, and then all these basically things, when we do try to analyze the static stability, we all are concerned about positive definiteness of the potential energy. Okay. So then that has been generalized to the topology of the energy surface, including kinetic energy for dynamic, and then we synthesize something called Lyapunov functions. Okay, that was also given by Lyapunov. So there are alternate choice of Lyapunov functions that include the potential energy as well as kinetic energy, and these things were developed. Okay, later there have been theory for the, and there are lots of misunderstanding, initial understanding, where see what we consider traditionally the forces have some direction, but there can be forces which basically changes its direction under the deformation of the system. For example, a column subjected to follower force. So force means a follower force is one which follows the tangent of the teeth. So initially, this problem was not solved until Bolodin, and in 1963 and others they tried to solve it. So initial static approaches all failed, because unless and until you consider inertia, this is one of the non-conservative systems. So all elastic theory cannot be applicable. So by incorporation of the inertia and then subsequently formulating the equation, they solved the instability problem of column under follower force. Now the very famous 1940 Tacoma Bridge collapse, it was investigated by von Karman, the great aeroelastician, and great fluid dynamist. So he submitted a report to the Federal Work Agency on Tacoma Bridge collapse, and subsequently there have been lots of surge in the aerodynamic instability of flexible bridges, namely cable stayed and cable suspension bridges, and then people, by now it is well understood that what really happens for case of aerodynamic flutter of bridges. And then mostly for stability analysis we try to use energy function, because that is the most standard approach and then most convenient, because it is very easy to work with the energy being a scalar function, right. So we try to ensure the quadratic form of the energy potential function's positive definiteness, okay, and then we try to see the tangent stiffness matrix in case of nonlinear behavior, that way the tangent stiffness is positive definite. That basically ensures that the Hessian of the potential energy functions is greater than 0, right. Now with this, based on this energy approach, stability behavior can be classified in different systems. We will study each of that. There can be stable symmetric bifurcation, unstable symmetric bifurcation. Whenever there is a loss of stability, what happens? A system attains a alternate equilibrium configuration. So the stable equilibrium bifurcate into stable or unstable equilibrium. Okay. So that's what the bifurcation is associated to the buckling, right. So you will see stable bifurcation, symmetric bifurcation, stable asymmetric bifurcation, or stable symmetric asymmetric bifurcation. So these different classes of behavior we will study, and along with that, depending on the system, there can be imperfection sensitive or imperfection insensitive, meaning in presence of geometric imperfections, this system behavior can be drastically different. They can lower down the critical load significantly, and that is called imperfection sensitivity. And there are universal laws for this imperfection sensitivity that were developed by Coiters. So, and those are called weak and strong sensitivity, half and 2/3 power law were derived. Now, there are other system in which are nonlinear system from the very beginning, they in which the bifurcated system is not in the immediate vicinity of the when a column basically buckles, it just achieve a little deflected configuration, right. But there are system like von Mises truss, we will see, or arch, which on buckling they will immediately jump into a different configuration further apart. So, there is a huge gap between the alternate configuration and the previous configuration. So, those are called snap through behavior. So, that we are going to show, but there those systems are nonlinear system and they cannot be meaningfully linearized, that we are going to demonstrate. Along with that, there are other sections in which those are thin wall section, where the along with this Venant torsion, there are warping torsion, meaning those cross section deform under torsion. So, you have to consider the associated force variable to be bi moment. Okay. Those of which you are familiar with the advanced structural analysis of a thin wall section, you might know what is bi moment. So, then there are formulation for lateral and lateral torsional buckling, and there are solutions. Okay. All these things, okay, that we are all developed. Then what we are going to do, now comes the the more intricate things, which is buckling of cell. So, buckling of cell has a very fascinating history, okay, and it is a long gestation period. Okay. So, initially this Lawrence, Timoshenko and Southwell, they started estimating critical load for pressurized spherical cell and axially compressed cell, because these are the two most common example, axially compressed cylindrical cell and spherical cell under external pressure. Okay. So, they find out some solution, of course, based on linearized stability theory. By the time nonlinear theory were not very well developed, and then what they saw that, oh my God, the experimental critical load that they were getting is very low comparing whatever was theoretical prediction from the linearized stability theory, 3 to 8 times smaller. Can you understand the difference? So, then that created lots of confusion among the mind of researcher, and so cell buckling always remain a very important area of research. Okay. And it is a very interesting problem, okay, even today also. And then you will see that cell buckling community is there. So, the people leave contributions are always documented there, and they had a great collections of the literature. So, then it was first the von Karman, once again the great fluid dynamist, and and his contribution, it was the von Karman 1941, and then Cian. They gave the meaningful explanation to settle out this huge intense dispute or intense debate that why this thing is happening, and they attributed it to the high non-linearity that is involved in the system. Unlike all the system like beam, column or even frame, all the system, what happened is that the effect of influence of non-linearity is not that significant on the critical load. Okay. And but here what happened is that from the very beginning non-linear plays a very important role. Even linearized analysis, whatever you are going to get is a bunch of buckling mode and a bunch of buckling mode, because it of course it is a you will have multiple buckling mode, right, and they are all coupled by geometric nonlinearity. So, they will interact, and as a result of these modal interactions it causes a reduction in the critical load, and all these buckling modes are basically they show high asymmetric bifurcation. So, they are highly imperfection sensitive. Okay. And then comes the general post-critical theory by Coiter. It was initially written in Dutch. In my lecture later you will see I made a mistake, I referred it to German, but it was written in Dutch, later it was translated. Okay. And then of course subsequently Armour, Tennyson and Chan, they are the great minds actually which throw light in this debate, and they started providing a meaningful explanation of this huge disparity between the experimental and theoretical load in cell. Roda was the first to show that critical load can closely approach by experiment for nearly perfect cells. So, what happened earlier days, experiments were difficult to conduct because the way you fabricate a cell, that has lots of bearing on the on the critical load you obtain, because all these primitive fabrication technology, they used to have lots of imperfection in the cell geometry. I mean, lots of imperfection means whatever little that was significant. But today with 3D printing this and that, you can have a very like cell geometry which is virtually perfect. So, if you do so, then you will see that asymptotically with a reduced magnitude of imperfection, that can asymptotic approaches to the right theoretical value. So, that was a great observation. Okay. So, not only the multiple closed space buckling mode, they are, see the buckling mode, you will see that when we linearize, there are critical load which are very close to each other, and because of their this closeness, or because of their multiplicity, even single, there can be two modes which are the same buckling critical load, they interact, and not only that, there are huge role of pre-buckling nonlinearity and the imperfections as well. So, that is still a very fascinating subject. Okay. Even with finite element today, see today's stability analysis, all we rely on finite element, because we have this commercial software, and that becomes $1 billion industry, and we all try to use, because it is simple. Gone are those days where people used to derive lots of complex differential equation and we analytically used to try, So, you have much less effort today, but even with finite element, Budhansky and Hutchinson, they demonstrated that it is extremely difficult to capture the theoretical load, because we have very inappropriate representation of the exact imperfections. Traditionally imperfections were assumed to be self-affine to the buckling mode geometry, but it is not. Sometimes it is random, and that is why probability theory plays a very important role in defining this geometry, and that is what people are doing today. So, in order to avoid these things, empirical corrections were given on the theoretical critical by multiplying with a reduction factor, which is called knockdown factor. In fact, this formula knockdown factor formalism is used, this formulation is used by NASA in US, for all their space program to use KDF, which is geometry dependent and dependent on the loading, to have a KDF for different geometry and loading condition of cell. Okay. This is used. Then later there have been shallow cell theory from the assumptions that there are these buckles which are formed, the rise of buckles on the cell surface can be considered as shallow, and using that Donnell defined a 8th order partial differential equation for the cylindrical cell, which is very famous Donnell's equation for the buckling of cylindrical cell, and then later that has been generalized by other like Mustari and Vlasov. So, that is, they give 8 first order PDE for any general cell geometry. Of course, cell geometry itself, to define, you need to have lots of differential elements of differential geometry, you have to understand that, but ultimately it gives a Donnell, Mustari, Vlasov equations for that. And then of course, there are, depending on the what material like sandwich or composite plates and cell, there are interaction between the global and local mode. Even then global and local mode interactions are also there in column and frame. See, for example, if you have a reticulated column on the last column, okay, there can be interaction of the global mode and local mode. I have presented those things in my lectures. Then there are inelastic stability, elastoplastic stability. So, the first it was attempted by Engieser, once again the one scientist who investigated the effect of shear deformation on buckling load. So, then he told that inelastic column, you can just replace the formula pi square EI by L square, the critical load, by E should be replaced by the tangent modulus for the inelastic analysis. But then later he reversed himself, 1895. He told no, let us use for the geometry dependent weighted average for the loading and unloading modulus, which is was referred as reduced modulus. But then people saw that there was huge disagreement between the theoretical whatever was given by reduced modulus and with the actual experiment on the aluminum alloy. Yeah, of course, aluminum alloy was mostly used by aerospace industry because of the lightness. Okay. Then in 1947, Sanley he used a inelastic simplified model for the column, and he demonstrated that while whatever was the original proposition of Engieser, using the tangent modulus, that is the correct proposition. Okay. And because the assumption, there was a problem in the assumption, column does not buckle at constant load, but at increasing load. And because whenever this inelastic things, you can have a hardening kind of behavior as well. Okay. So, that was a main difference. Okay. So, tangent modulus was found to be correct. Then later it was generalized by Hill-Shanley's theory. So, Shanley's theory is very well acclaimed, and later it was generalized Hill for elastoplastic structure, not only for the column but any structure. So, Hill's theory for the inelastic buckling or elastoplastic buckling of structures. Okay. There are huge influence of the locked in stresses or residual stresses that has been demonstrated by huge disparity between the theoretical load and then the experimental load in hot rolled sections. So, that was attributed to the residual stresses. Okay, because there was a huge difference between the tangent and reduced modulus load. Okay. So, here people have that has also important bearing in formulating the code provisions, because in code when you deal with these rolled sections, you need to take into account. So, there are some modifications has been done. Okay. Not only that, see, it is not that always uniform yielding will happen. There are instances in which plastic strain localizes. For example, whenever you do a tensile testing, you see that there is Lloyd's line that falls, right. So, shear band. So, those are some kind of localization of plastic strain, necking kind of behavior. So, sometimes plastic strain localization instability is also important. Okay. Other than that, so what we have seen that here, see, all the elastic structure is fine, but inelastic structure include basically dissipation in the form of sometimes inelastic dissipation of energy, because this shows hysteresis is there. So, loading unloading paths are different. So, that is what they lead to dissipation. So, that can be best accommodated in using irreversible thermodynamics. Okay. And then you can use a different alternate energy functional like what we have learned in thermodynamics, Gibbs or Helmholtz free energy functions, and then thermodynamic criteria has also been developed. See, in stability analysis using energy functional, you have a Hessian of the energy functional, like for equilibrium you have the minimization of potential energy, and then second order of potential energy, or for multi-degree of freedom system the Hessian of the potential energy functional, determinant of that must be greater than 0 to be the stability criteria. So, whatever was done using energy functional, that can also be equivalently transformed into thermodynamics context. So, positive definiteness of the tangent stiffness matrix is shown to be equivalent to the negative of the entropy increment. You see, we cannot measure entropy, but change in entropy can be measured, right. We can clearly find out that the entropy increment for a system, if it is negative, that is equivalent to the positive definition of tangent. So, you see the thermodynamics for inelastic system or the system which has lots of dissipation, thermodynamic framework can be used very efficiently to tackle the inelastic stability aspect. Also, there is another important thing which must be mentioned, that you see sometimes whenever there is alternate bifurcation, so equilibrium path sometimes bifurcate into alternate equilibrium path. Okay. So, multiple branches occur. Now, which branch should be taken by the structure? That is a problem in numerical simulation in finite element. So, instead of using the energy formulation, if you use this in thermodynamic formulation, then you see you can very easily find out which path to be followed based on maximum of the second order increment of entropy. So, that is another thing that has been given. Now, there are localization instability due to damage. So, these are a material. So, material instability, because what happens is that sometimes damage localization happen due to strain softening, like concrete after yielding it basically there is softening branch, it does not strain harden. So, for this you see descending peak, there is loss of positive definiteness due to softening, and then you will see for this elastodynamic boundary value probably changes from hyperbolic to elliptical Hadamard. These are the important things that has been, and there is something called single acoustic tensor that can be formulated using the constitutive matrix and using this orientation of the whenever there is strain localization, there is a jump, discontinuity in the strain field. Okay. Displacement will be continuous, but the strain will be discontinuous. Okay. So, those things can be find out by searching for the singularity of the acoustic strain. So, that can also be one kind of instability, of course, in terms of material instability. Then instability due to propagating fracture, there is single fracture, multiple fracture. So, these are all instability induced by crack, propagating crack and others, right. And then time dependent behavior by viscoelastic and viscoplastic structures. So, viscoelastic means you see there is equivalence principle. So, you just replace the modulus of elasticity with the viscoelastic operator, okay, and then you solve the equation. Of course, it will be time dependent, but here the important thing is that there is a long time buckling problem, because with time the buckling load is going to change here. So, the way it is formulated by replacing the elastic modulus with the respective viscoelastic operator, which can be expressed either in rate type using differential equation or integral type using a integral equation. So, there has been referred to Friedel, who was also a big name in structural safety. So, it is load that is not important, rather the time must be large enough, so that to reach the critical load. So, for a viscoelastic system, the time required to reach that critical load of that should be long enough, okay, comparing the design life of that way you ensure safety of the structure. So, similarly for the viscoplastic, only difference is that here it is once again the similar approach, that you need to have ensure that finite critical time for the deflection. So, whatever deflection in viscoplastic material, what happens is that the deflection it increases with time, like strain get accumulated. So, that is what we refer as creep, and then it is due to viscoplasticity. So, these things are also very important. Of course, there is this inelastic, because viscoplasticity the yielding happens, and then every time instant there is a change, right. So, there have been model for that, and this is very extremely important for the aerospace engine and others, where the material shows viscoelastic behavior at the elevated temperature. Okay. So, you have to ensure that first critical time for the deflection triggered by infinitely small imperfections become finite. Okay. So, a small imperfection can have a huge implications for the viscoplastic, because it accumulates, right. Then there is another approach, what we all were talking about in the tangent stiffness matrix, but then tangent stiffness matrix for finding out the geometry, its Hessian and others, right. You need to have potential energy that must be quadratic, correct until quadratic term in terms of displacement when you express. However, there are alternate definition of finite strain tensor, because when we deal with finite deformation, there are alternate definition and conjugate definition of finite strain tensor, like Green Lagrange, Biot, Henke, and that must be correct up to second order, right. But all these things used to give different expressions because of this, for the stability analysis for the 3-dimensional continua, and this inconsistency was leading to lots of confusion. See, this is not important for plate, cell, or beam column. Why? Because the second order finite stress tensor depend only on the rotation, for the these things del W del X, right. So, for that is why this discrepancy was not important for plates and cell and other, but for the 3-dimensional continua, when you want to study surface buckling or buckling of the 3D continua, then this you have to make sure that potential energy function quadratic terms in terms are expressed in terms of displacement, but then all these alternate strain tensor they are producing different result, but equivalence between all these things has been proved by Bajan, okay, who was one of the prominent figure, okay, because there are huge geoformulation, there have been formulation presented to remove these discrepancies, okay. So, those of you who are familiar with finite deformation theory will try to understand these things, we will not cover this thing. So, the conclusion is that by now elastic structures, stability of elastic structures is well understood, and refinement is still expected for the elastic stability as well, especially with the advent of new structural configuration and material behavior. But greater challenge is today is that stability in presence of material instability in the form of fracture, in the form of damage, softening damage, and strain localization, those things, okay. and coupled problem where the not only the mechanics, but mechanics is coupled with thermal phenomena, mechanics is coupled with chemical kinetics, mechanics is coupled with the electromagnetics. Okay. So, for these stability coupled problem, these are still remain unsolved, and then I think more thoughts are required for this, and people are doing that. And also for the long term degradation, for example, under chemomechanical degradation. Okay, what is happening? That's, and along with that, of course, very important is the probabilistic treatment of stability theory. Why? Because no matter what you do, imperfections will always be very important, especially for structures which are imperfection sensitive. Even there exist a large classes of structure which are imperfection sensitive. And then imperfection, when you want to describe physically, you need to use probabilistic means. Okay. So, that is another important thing. So, with these things reasonably we reviewed that what is the need of structural stability, I mean, and what great minds has been done, have been doing, and over the past more than 2.5 century, starting from 1744 by Euler and today's with the latest development. Okay. Now, with these things we will start, but before that I will just refer to several books for this, which are important, for you. So, there are many books, good books, for the general theory and concept. Of course, Timoshenko and Gary is the one which is a classic in the theory of elastic stability. Then there is a book by Alexander Chazes, Principle of Elastic Stability. I refer it, it's not that the years are given, it may not be correct because there have been a newer edition, but that doesn't really matter. This is from McGraw-Hill, this is Printesol, and then there is this book Bajant and Sedol, in which I follow. Of course, there are in certain places you have to be cautious, but this is, I mean, I treat to be Bible of stability. This is very good, very thick, and that cover almost all aspect of stability. Maybe little difficult to follow with unless and until you have a background, in a reasonable background in structural dynamics, reasonable background in finite deformation, in elasticity, plasticity, little bit of background on fracture, little bit of background in damage mechanics. All this background, if you don't have, you cannot follow all of it, but definitely whatever we are going to cover, you can definitely follow. And then there is a good book by Smith says, in Introduction to Elastic Stability by Printesol, and then Bruce and Almorth, this is a very good book. Of course, I think they lack new edition, but this is one of the very good book what I sometimes consult, buckling of bar, plates and cell. Now, all these things mainly with the stability of, theory of stability. Of course, they refer time to time, but briefly to the design thing, but if you want to have a comprehensive treatment on the design guidelines based on stability theory, then you must consult Galambos, that Guide to Stability Design Criteria for Metal Structure. This is a very good book, and only for dynamic stability, not that all these books doesn't cover dynamic stability, but if you want to go to explore more details, then Bolotin, these two books, or Bolotin non-conservative theory of elastic stability and dynamic stability of elastic systems. One is Pergamon Press, and another Bolotin, one of the prominent name in dynamic instability. Then for the finite element method, of course, now today's stability analysis all depends on finite element. Everybody want to do simulation rather than dealing with the complex differential equation, and that's so their solution is even more complicated, one of those days. So, you have to be cautious with using finite element theory, because sometimes it can be very, very misleading unless used with proper judgment and proper clarifications. Okay. So, finite element method, of course, you have this very simple book which we follow for finite element Cook, Robert D. Cook, Malkus and Klesa, Concept of Application of Finite Element. But along with that, there is another book by Sams which is also good, and Rubinstein, this is a simple book not only on structural stability, but he also covers static dynamics and stability aspect. Rubinstein, for advanced things which you don't require for this course, but nevertheless I thought I will put it, Thompson and Hunt, they are also he contributed very huge they have huge contribution in development of the stability theory, Thompson and Hunt, and their paper you will read, A General Theory of Elastic Stability, and then Leifwolge and Ness. All these things are for the advanced treatment. So, with these things I will stop here. So, we will start with this, the stability class, and I will use Blackboard, for this. So, this is the first lecture along with this. So, first lecture on stability of structure. So, the first lesson to learn actually for stability of structure is that we discussed actually is we were concerned about in all other courses, it is the equilibrium, right. In civil engineering system, structures, whatever we are concerned about the equilibrium, right. And in equilibrium, how do we, what we do? We write down the equation, equilibrium equations in equations in undeformed configuration, right. That's what we write, deformed configuration, right. Right. That's what we write. But in stability, there is little difference. Okay. In stability, the first lesson in a stability class is that we write the equilibrium in the deformed configuration. We have to analyze equilibrium in deformed configuration, deformed or perturbed configuration. I will try to explain why. Perturbed configuration. Why that is so? Let us go back to our school level physics. Okay, when we have learned the concept of equilibrium, and then we are given, so whether a system is in equilibrium or not, that was the zeroth order information or first order information, right. And then once we know that system is equilibrium, we have to inquire that whether that equilibrium is stable or unstable or neutral. So, that is a higher order information, right. So, equilibrium have three different things, whether the equilibrium is stable or equilibrium is unstable or there was neutral. So, what we have learned in our school level, so from there I will, so you see we have made use of this simple example. Consider a bowl kind of things, right, and then we are putting a small ball here, right, here. Now, this small steel ball, maybe any ball, okay, made of, and this ball is in equilibrium because its weight is acting, and so downward and it has a upward reaction, right. So, R is basically this weight W and the reaction R, right. So, R is equal to W, right. So, it is in equilibrium, right. Now, what we want to know, we want to study the nature of equilibrium. So, what really happened to this ball? So, how will you see that whether the equilibrium is stable or not? So, for that, what we did? We want to perturb it. So, we took it here, we have given a little perturbation and wanted to see whether it come back to its original configuration or not, right. You see that? Or we perturb it here and then we see whether it comes back to its original configuration or not. In both the cases, whatever perturbation you see this perturbation can be expressed in terms of theta, angle theta or angle theta, whatever, right. In both the cases it is coming back. Why it is coming back? Because a component of its weight mg, that is basically giving a restoring force to come back to its original configuration, and that is why the equilibrium is stable. So, but in order to see the nature of equilibrium, what we are doing? We are perturbing it. Do you see? We are perturbing it to check what its behavior in a deformed configuration, and that is what I am taking. The stability, equilibrium, we need to assess in deformed or perturbed configuration. So, that is the first difference. So, until now, when we were only concerned about the stability, equilibrium itself, we do not care about the perturbed configuration, but here we have to care about the perturbed configuration or deformed configuration, and then we have to write down the equilibrium equation, right. Similarly, if we consider the same bowl, but it is put in a concave, okay, here it is convex, here it is, and then you put the ball over here, right, and then what is going to happen? You see what is going to happen now, if you just give a little perturbation, this fellow will come and this fellow will diverge, it will fall. That means it is not coming back to original configuration. Why? Once again, the component of it weight is basically allowing it to diverge. So, this is unstable configuration. Once again, when we are ascertaining that it is the equilibrium is unstable, we have to perturb the configuration, and this perturbation is given in terms of theta, right. Now, there can be a third possibility that there is a plane, and on the top of it there is this ball is kept, and here wherever you put the ball, it does not really care, it will stay in its in position. So, this is referred as neutral equilibrium, right. So, equilibrium is the first order information, and then higher order information is the nature of equilibrium, whether it is stable, whether it is unstable or neutral. And the thing we learned that in order to study the nature of equilibrium, we have to see its behavior in the deformed or perturbed configuration. Okay, so that is the first lesson of stability. Now, the way we are going to study first and most, all of you can recall that maybe that will come later, but here what are we going to do, that of course when you study, can we define some energy, can we define something with some measure of the stability, nature stability, or some we can quantify it mathematically? Yes, we can. What we have seen, most convenient way to analyze a system is in the elastic system, and that is to the system is equilibrium. You can recall, right, so we have our energy approach. In energy approach, what we did? Energy approach we have all learned in our strength of material or even in structural analysis, right, that all equilibrium is based on minimization of the potential energy, right, minimization of potential energy, That means potential energy we are defining in terms, we are denoting using pi, potential energy. And what is potential energy? Is the strain energy minus work done. You know how it is coming. So, this is strain energy, strain energy minus work done, right, minus work done. So, potential energy for a elastic structure is given by strain energy minus work done, right. And you know how this is coming, that the strain energy of course is a component of the energy stored in the system. If it is doing some work, that means this work, the energy is dissipated. So, that is what it must be subtracted. So, that is the basis, right. So, once we have potential energy functional, then for equilibrium, what do you know? Minimization of the potential energy. That means, what does it mean? Del pi with respect to what? Del pi by del u is equal to 0. I am assuming that its degree of freedom is given by u, right? U is the degrees of freedom. So, a system can have certain degree of freedom with. So, when we are writing potential energy, pi is a function of what? It is a function of course, the force being applied on the structure and then its displacement. And now, force is related to displacement anyway, k into u if it is elastic structure. So, I can express it just solely as a function of the displacement. That is what u is the displacement. So, I can write for minimization del pi del u is equal to 0. So, that is the minimization of the potential energy, right. So, if minimization of the potential energy is referring to equilibrium, then we will see that whether the equilibrium is stable or unstable can be find out by scrutinize or by investigating its higher order derivative. How? So, what we see that it is a function of u. U is the generalized displacement, okay, along different degrees of freedom, okay, degrees of freedom. So, pi is a function of u, the potential energy function pi is a function of u, and we are giving a perturbation. So, u we can put it U0. U0 is the initial configuration. U0 some initial or datum, initial or some datum configuration, right? Or it is in datum configuration. So pi U0, and then when we are giving a perturbation, then it is being U0 plus delta U. Delta U is the perturbation displacement, right? Displacement, So what is happening in due to perturbation displacement? Now, can we use, so we have learned to use, we are trying to express everything in terms of potential energy. We use potential energy functional, we are giving by perturbation because we know that we have to perturb it. So, can I use Taylor series expansion around this datum for U0 plus del pi del U at U0, delta U plus 1 by factorial del 2 pi del U2 delta U square plus whatever. Now, I am assuming that datum, we can assume that at datum we can choose the datum, we choose such that, the datum such that our potential energy in the datum is 0, U0 is 0. How it is 0? For example, you see, if you consider this concave bowl and then at the below we are putting the ball and then we are treating that at the lowest point to be the datum, then this is 0, right? So, this is 0. If this is 0, then what we have seen for equilibrium, minimization of the potential energy, right? So, minimization means this is also 0, right? Minimization of the potential energy, right? Fine. Now, you see, so a system is in this configuration and then we are perturbing it to another configuration. Now, if the system is, if I am stable, then I will not go to that configuration, right? Because when I will go this configuration, if it lead to a energy increment in energy, potential energy, that means I will see every system try to attain its the minimum potential energy configuration. So, if when I am being perturbed from here to there, if there is an increase in energy, that means that configuration is not conducive for my move, right? So, how that is? So, if that, see, delta U square, this is always positive, delta U square, this is always positive, right? This is always positive, always. So, if we can clearly see, if del 2 pi del U2 is greater than 0, that means the system is stable. Why it is stable? Because by perturbing, you are taking it to a configuration in which its potential energy is increasing, and all the system try to attain the minimum potential energy configuration. So, this greater than 0 is a condition for stable equilibrium, right? So, that means this configuration the system will not go, it will try to remain in its U0 configuration, right? However, different, that means if del 2 pi del U2 is less than 0, that means when it is going to U0 to U0 plus delta U, if there is a reduction in the potential energy, that means it will try to attain that, because by doing so it is minimizing the potential energy. So, it will always try to move that there, that means whatever is the equilibrium at U0, that is unstable. Clear? And now, if del 2 pi del U2 is 0, that means by perturbing from U0 to U0 plus delta U, there is a no change. So, that it does not really care whether you put U0, it is neutral equilibrium, right. So, I hope that all of you understand that why this is associated. So, you can clearly see that the first case here, you see that is here, where the ball is here in the lowest position, right? You are taking it to this position, it will clearly come here. Why? Because when you are taking from here to here, there is a positive increase in potential energy. So, del 2 pi del ut is greater than 0. This, when it is here, when it is here, from here you are perturbing it to here, it is a reduction in potential energy. So, del 2 pi del ut is less than 0, and then for the other. I will just try to do it using so this is for a system which is single degree of freedom, right? This system I am considering that u0 is the only displacement quantity, that means a single degree of freedom. If I generalize it for multi-degree of freedom system, what will happen? Generalize it, okay? Generalize for multi-degree of freedom system, multiple degree of freedom, of freedom. Of course, this will freedom system. So, then what will happen? You see that here is the potential energy, the only thing is that u0 will be a vector because it is multiple u01, u02, u03, and then your perturbation will also have delta u. Of course, when you perturb it, you have to keep in mind that you have to enforce the enforce using the boundary, you have to maintain the boundary conditions, right? There must be admissibility, right? So, here it is pi once again u0 plus del pi del u, here it is u0. Of course, there this is a vector, del pi del u is a vector, here please note that. So, when I am writing del pi del u, this is a vector delta u, and then plus 1 by factorial delta u transpose del pi del ui del uj 0 delta u. Higher order term we do not consider, not that it cannot, it should not be considered. Please note that if this is 0, that means if it is non-decisive, inconclusive in terms of del 2 pi del u, then you have to look for higher order derivative. Please note that, okay. But if it is there, so just we are omitting the higher order term does not mean that those are irrelevant. There are systems in which the stability cannot be ascertained using second derivative, those will be vanishing. So, then you will show using solved example that then you have to look for higher order derivative, 4th order, 6th order, something like that. So, here you see, so minimization of the potential, and so if the datum is taken to be 0, minimization of the potential energy, this gives delta u, anything, it can be positive, negative, it does not. So, minimization of the potential energy makes your that del pi del u at u is u0 is equal to 0, right. This is minimization of the potential energy, okay, that ensure that the system is in equilibrium. So, this is the first order information, that means the system is in equilibrium. Now, the higher order information, that means this is the higher order information, right, higher order information for a multi-degree freedom system. So, here what will happen? Of course, this is del 2, this is a matrix, this is called Hessian matrix. This is called Hessian of the potential. Those of you who did Hessian matrix, who did optimization course, you will know, because this is used in steepest descent method for optimization to find out the minimum point, okay, for the numerical search technique for the Hessian matrix, where now this is a matrix for stability condition will be this matrix. So, I am defining that Hessian H for the potential. So, determinant of Hessian must be greater than 0 for stability, and all its principal minor, you know what is minor for a matrix, right? Principal minors must be greater than 0 for the stability. For the stability condition, the determinant of the Hessian matrix must be greater than and all its principal minor. Principal minors meaning respective to principal minors corresponding to the diagonal term. If you take the diagonal term, then whatever the submatrices remains, the determinant of that, right? So those are principal minors. So if the Hessian greater than 0, all of principal minor greater than 0, then it is stable. If the Hessian matrix less than 0 and principal any one of these principal minor less than 0, then it is unstable. And if all these vanishes, it is. So you understand from the single degree as well as multiple degree. Here the derivative of the potential energy function, here the determinant of the Hessian. Once again, this is nothing but the second order derivative of the potential energy function, but the only problem, because you have a multiple degree of freedom system, you will have a varying combination of the among the degrees of freedom, right? 1, 2, 2, 3, 3, 1, something like that. So you can solve if you want. I mean, you can solve a simple system. So this system, if you want to solve mathematically, if you maybe here the ball is put, okay, this ball, and then you see that. So here you are, this I am assuming this is the radius of curvature r, right, and then it is perturbed to a different configuration, right, here, and it is going there, right, this is r, this angle is theta. The first step is the perturb the configuration, perturbing it. So I am assuming that this I am treating as datum, this point, okay, this is datum, because that means here when it is here, then it is a zero potential energy, right, zero potential. So how potential energy is defined here? This position will move here, right. So what is the potential energy? M into G, the work done, M into G. I am assuming mass is M, G is the gravitational acceleration, right. And then this distance is nothing but this is r and this is r cos theta, r minus r cos theta, right, this distance, right, this distance. So that means r 1 minus cosine of theta. So mg r 1 minus cosine of theta. Now we see for equilibrium, del pi del theta is equal to mg r sine theta. And of course, if you want to make it 0, then means what? Sin theta is 0. So theta is 0. That's the equilibrium. You see that? Equilibrium you will get automatically. You see? So it will be equilibrium when theta is equal to 0, right? Now you are for theta non-zero, non-zero theta. Then for stability, del 2 pi del theta 2 with a single degree of freedom system, because everything potential energy is expressed in terms of single variable, displacement variable theta. So double derivative is what? mgr cosine theta. So mgr cosine theta. So I am assuming if theta is small, that means for small theta small mgr, right. So theta small, very very small, small quantity, and this is always greater than 0. So that means it is stable. Understand that? Stable. So that way we can prove that this is stable, right? Similarly, you can also solve the problem where then for the problem here where it is concave surface, right? Here you just write the ball, keep that, then you are putting it here. So from here you are giving here, So I am treating maybe this to be datum, here from here. So what is happening from here to here when you will get what is potential energy? Potential energy is what? Potential energy will be, if I treat this to be datum, this point, then if this is r, so r, this angle is theta, so it is mg r cosine of theta. This is the datum, this point, point of curve, the center of curvature, right, mgr. Then del pi, so del pi del theta mgr sin theta minus sin theta, so 0. Here theta is equal to 0 is the equilibrium, right? Equilibrium, and double derivative del 2 pi del theta 2 is minus mgr cosine theta is minus mgr. So always less than 0, it is unstable. Do you see that? Unstable. And then if you derive any system in the flat plane, here potential energy will be what? mgh, and then difference always it is 0, del pi del 2. Okay, so it doesn't really. Okay, clear? Now we will solve problem for the multi-degree of freedom system in the next class, but before that, so one more thing that I will just try to emphasize with what we have learned from our undergraduate course, undergraduate course, we know how to determine the critical load for a column, and critical load is column due to buckling. Okay, so here we are going to consider the same with a little more insight. So for that, if we allow it to deform, this is something like this, right? P, load P is given, this is hinge and that is also hinge. I am assuming this is to be length L, and I am assuming this is flexure rigidity I. Now, of course, we have to allow translation for this. So then P this is hinge column, right? This is hinge column, right? Hinge. So we will write down. We will try to study its behavior, stability behavior. Okay. So of course, the one way to do this is following the potential energy approach, right? But we have not used that approach in the undergraduate. I will. So undergraduate, what you have done? We have written down the we have perturbed it. So we have perturbed it means we have assumed that, well, let there be this Wx and x is assumed in the x, right, along the longitudinal axis. So when I am perturbing, once again, the first lesson for stability analysis to perturb the configuration. That's what we are considering. Okay. Then what we are doing? Because of this perturbation, there is an additional bending moment that is going to come. So if this load P is there, P, so P into Wx, that is the bending moment, P into W, right? And that is nothing but what? Minus Ei. Bending, you assume that our deflection is infinitely small, the perturbed configuration is infinitely small, we are assuming small deflection, right? So then we can write it. So that's what d2w dx2 plus P upon Ei, W is equal to 0. So P upon Ei is then means d2w dx2, and we are defining P by here, lambda square is equal to P by Ei, lambda plus lambda square W is equal to 0. So it lead to a second order differential equation, right? We know how to solve an second order homogeneous differential equation. Of course, we have the boundary conditions. The boundary conditions, what are the boundary conditions? At x is equal to 0, W is equal to 0, no deflection because it is hinge. At x is equal to L length, deflection is 0, right? Two boundary conditions. So second order equation, two boundary conditions, both are expressed in terms of W, that is permissible. So how to, the solution of this differential equation, as you see, A cosine of lambda x plus B sine of lambda x, that we know, and it is homogeneous equation, so there will be no particular integral. When you enforce the boundary conditions, that x is equal to 0, W is equal to 0, x is equal to 0 means A into 1 plus B into 0, so essentially A is equal to 0 and W is equal to B sine lambda x, W is equal to 0, B sine lambda L, B sine lambda L is equal to 0 means lambda L is equal to n pi, where n is equal to 1 to 3, where lambda is n pi upon L, or lambda square means P by EI is equal to n square pi square upon L square, or P is equal to n square pi square EI upon L square. So, when n is the natural number 1, 2, 3, you see that this is the critical load PCR. What we see? There is several things to note here. Stability analysis. Here, see buckling, we are finding out the stability alternate configuration. Although right now we are not showing it whether it is stable or unstable. What we want to find out, that whether is alternate configuration exists or not. Buckling is one such thing in which there is a alternate configuration exists. That means from fundamental path at x is equal to w is equal to 0, it going into a bifurcated path, buckling, because this is bifurcating to a alternate configuration. And also another thing is that it is also called symmetry breaking, because after buckling it will go only in one direction, it cannot go to other direction. Whether it is right or left, it matters there, but once it buckle, it will try to diverge in one thing, right? And that led to what is this equation? This is homogeneous equation. This is nothing but a, from here when I am writing here, so this thing, this is nothing but a eigenvalue problem, and these are called eigenvalues. So, these eigenvalue problems are in terms of what? In terms, both are, see, these are the homogeneous boundary condition, and homogeneous boundary condition lead to eigenvalue problem. Okay, and these are trigonometric eigenvalue problems. So, eigenvalue problem. You will see all these stability analysis will lead to a eigenvalue problem if it is linearized stability analysis. There are non-linear stability analysis which will be different, but for linearized stability analysis will lead to a eigenvalue problem, and that's where we got it. So, here how the system is linearized, we are assuming the deflection to be infinitely small. Okay. However, if you want to study the non-linearity, then we have to consider large deformation, that we are going to discuss. Large deformation means d2w, dx2 is not the curvature, okay, it is not the curvature, rather curvature will be given as d theta ds, and where this is s and this is x. So, we will be distinguishing between x and s. Here we are don't distinguishing between this x and this x, because both are same, we are assuming, right. That is why this non-linearity is being linearized here, okay, but that we can put in. And we can also define energy potential functional here, that maybe subsequent class we will say, okay. But before that, we are going to do a multi-degree of freedom system and stability analysis, and we will try to first use the potential energy approach, because that itself will give us a huge insight into the problem, okay, and we will see various classes of system, and accordingly we will continue. Thank you very much for today's lecture.